podcast series on synthetic biology.
We're the City of London iGEM team of 2024, and our goal here is to release weekly podcasts you can listen to anywhere at any time.
Today brings our final episode of the BioBasics season, and we're finishing with a super exciting episode on enzymes. Let's get started.
But before we do that, remind me again, what were we talking about last episode?
We were talking about macromolecules, so that's carbohydrates, proteins, etc.
Yeah, I remember now. And we also mentioned that some proteins can function as enzymes.
Exactly, and that's a perfect follow-up into what enzymes actually are. So we've established all enzymes are proteins, but not all proteins are enzymes. So could someone tell me what enzymes do? What is this enzymatic activity we've talked about last episode?
I know, enzymes act as biological catalysts.
Wait, but what does that actually mean?
Basically, it means that enzymes increase the rate of reaction of chemical reactions in our body. And this is essential to our functioning because all the chemical reactions in our body and other organisms would carry out way too slowly to sustain life.
I'm wondering, what are some examples of these chemical reactions in our body?
Respiration is a very important one that we've already talked about, taking glucose and oxygen and releasing ATP, which is essential to our daily functioning.
But let's zoom out for a minute. Generally, enzymes catalyze two groups of reactions, anabolic and catabolic reactions.
And the name for anabolic and catabolic reactions combined is called metabolism. And this is just the total sum of all chemical reactions that occur in our body.
I've heard so many people say, oh, my metabolism is fast, or oh, my metabolism is slow. So is that based on their enzyme activity?
It's actually a sum of a lot of factors: aging, muscle mass, exercise levels. I don't think it's anything in their enzymes or some people that make their metabolism fast, just other things about them. It's very multifactorial.
So if metabolism is an umbrella term, let's define anabolic and catabolic reactions. Anabolic reactions refer to those that build up monomers into polymers, whereas catabolic reactions do the exact opposite. They break down polymers, so when I say polymers, I mean the macromolecules that we've been talking about, into monomers.
And enzymes catalyze both types of reactions. An example of an anabolic reaction is making glycogen, a storage molecule we've mentioned from glucose. This requires many different enzymes.
So then, do a lot of examples of catabolic reactions happen during digestion, when macromolecules are broken down?
Exactly. One example is starch that we've eaten being broken down into maltose by the enzyme amylase.
Now, you've mentioned amylase as a specific enzyme, but I'm just wondering, how are enzymes named and is there a rule to it?
So enzymes are named after the substrate they break down, but with an ase ending. For example, amylase breaks down the amylose in starch.
So the enzymes that break down proteins are called proteases, and what breaks down lipids are lipases. It's really very simple.
I'm sure our listeners want to know how they actually work, though. How can something just increase the rate of a reaction?
So, for any chemical reaction to take place successfully, molecules have to collide with energy greater than or equal to activation energy.
Wait, hold up. What's the activation energy? Is it just the energy required to activate the reaction or something?
It's the minimum energy required for a reaction to take place.
So then what enzymes do is provide an alternate reaction pathway with a lower activation energy, so more molecules meet this lower energy requirement and the reaction can proceed quicker.
Wait, but I'm confused. If all enzymes perform the same job, how do we have specific enzymes for breaking down specific substrates?
Well, all enzymes have something called an active site, and this has a very specific shape and is complementary to one substrate. Only that specific substrate can bind to the active site of the enzyme once the enzyme and substrate collide.
So each enzyme can catalyze one reaction with one substrate.
This has a very funny name called the lock and key model of enzyme action.
But that's not all there is to it, is there? Something must happen after the substrate binds to the enzyme.
After they bind, what's called an enzyme substrate complex form. The enzyme then converts the substrate into the product, which could be the substrate broken down or the substrate built up to a polymer.
Then, since the product doesn't match the shape of the active site, it's released.
What I find amazing is that the enzyme's active site remains unchanged throughout the whole process. so the enzyme is never used up. It can just go about and catalyze more of the same reaction.
Wait, guys, hold on. I've heard this isn't the only model that explains how an enzyme works. What's going on with the induced fit model?
That one's a bit odd. It kind of suggests that the enzyme's active site shape isn't completely complementary to the substrate shape.
Wait, so is it saying that the active site changes shape to fit the substrate better once they collide?
Exactly, and once it changes shape, the reaction can then be catalyzed and the product's released as normal. It's very odd.
So, which model is actually correct?
It's kind of a mix of both. So some enzymes have really high specificity to their substrates, which would suggest the lock and key model. But other enzymes actually catalyze a number of chemical reactions, meaning that it must have a more non-specific binding site which changes shape.
Many scientists actually accept the induced fit model now because the way the active site changes shape while the substrate is within it could explain the stress placed on the bonds of the substrate, which means it is converted into the products.
Oh, interesting. It has me thinking, just like diffusion rate can be changed, are there factors which affect enzyme activity?
There definitely are. One example I can think of is increasing enzyme concentration. And this means that the rate of reaction will increase, since a collision between an enzyme and substrate is more likely, meaning more enzyme substrate complexes can form.
Surely that can't carry on forever though.
After a point, increasing enzyme concentration doesn't affect the rate of reaction, and this is because something else becomes a limiting factor, and this is most likely to be substrate concentration.
Okay, that makes sense. After a while, you can increase enzyme concentration all you want, but that'll just mean you've got all substrates binding and some enzymes that are redundant, I guess.
So then we have to increase substrate concentration, I'm guessing. So this causes more frequent collisions between enzyme and substrate, as expected. But then after a while, the enzyme active sites will all be occupied, and we call this saturated. So the addition of substrate molecules will achieve nothing as well.
Another factor that I'm thinking of is the temperature. As you increase this, both enzyme and substrate molecule have more kinetic energy, so therefore they'll collide more frequently and the rate of reaction will increase.
But there's a catch with this. If the temperature gets too high, it'll denature the enzymes, meaning it stops functioning.
Ooh, okay, but what does denaturing actually mean?
Basically, the high temperature that we were talking about causes the hydrogen bonds in the tertiary structure of the enzyme to break, which means the enzyme just fully unravels.
Oh, I get it. This unraveling changes the enzyme shape, so all the specificity of its active site is gone. That must decrease the rate of reaction a lot.
Think of the other factors.
An important one I'm thinking of is pH, but it's a bit different to all the rest. You can't just increase pH and expect rate of reaction to go up. Each enzyme has an optimum pH that it works at.
Can you give me an example?
Well, we've talked about proteases a bit, but there are actually two different examples in our bodies. One is pepsin, which is released into the stomach, and this enzyme's optimum pH is very low, since our stomach has hydrochloric acid in it and is very acidic.
And then you have trypsin, which is released into the duodenum. That's a higher pH environment.
So if you change the pH of an enzyme away from its optimum range, the rate of reaction will decrease. I'm guessing this is again because of our enzymes denaturing?
Exactly, yeah. Deviating from optimum pH breaks the hydrogen bonds within enzyme structures again.
Before we finish, we need to talk about competitive and non-competitive inhibitors.
I've never heard of them. Can you explain what a competitive inhibitor is first?
Of course. So a competitive inhibitor competes with a substrate. By this, we mean that it also likes to bind to the active site of the enzyme.
Oh, so they both want to bind to the active site. Yikes. So what about non-competitive inhibition?
They're slightly different because a non-competitive inhibitor doesn't actually want to bind to the active site. It likes to bind to another site on the enzyme called the allosteric site.
Once the non-competitive inhibitor binds to the allosteric site, the shape of the active site changes.
Alright, so I can tell that's bad news for the functionality of the enzyme. How's the substrate supposed to bind to the active site and form an enzyme substrate complex?
And that's precisely why it's called an inhibitor.
And that brings us to the end of this episode, and actually this season as well.
Thank you to everyone who listened to our BioBasics series. We hope you now know a bit more about biology than you did going in.
And as always, we'd love to hear your thoughts on what caught your attention and your favourite snippets over this season.
Don't forget to check out our Instagram and TikTok pages at igem_Cole for updates as to when our second season is coming. It's going to be more complex, but we promise to break it down.